So now we shall continue the discussion on perturbation approach. Okay. So firstly, we have started the non-degenerate perturbation method. Non-degenerate non-degenerate perturbation method. Okay. So at first we have an unperturbed system with Hamiltonian H naught say, and with its spectrum N naught satisfies the Schrodinger equation, unperturbed Schrodinger equation, En naught N naught. Okay, and then you apply some perturbation with corresponding Hamiltonian H prime, which is perturbing Hamiltonian, and with some regulating parameter lambda. Lambda is called the strength of the perturbation. The Schrodinger equation will appear as H, okay, with H function of lambda and n function of lambda equals to En depending on lambda. So both the energy eigenvalue En naught will turn into En lambda and the corresponding stationary states, that means the spectrum, the unperturbed spectrum was N naught and it will turn into some N lambda. And we have proposed, actually we have not proposed, the approximation scheme from perturbation theory. It tells that this n lambda will be basically the unperturbed state plus some correction term depending as the power law of lambda. So it will be lambda of n1, lambda square of n2, and so on. And the energy eigenvalue also in the same way, En lambda, which will be En naught plus lambda of En1 plus lambda square of En2, and so on. Okay. So now, and also you have H of lambda is equal to H naught plus lambda H prime. So assembling those relations, and you can put these outcomes in the Schrodinger equation, and you will find. Hmm.
EN1 EN2
Hmm.
এগুলো কি মানে EN এর কি EN0 এর ফার্স্ট অর্ডার সেকেন্ড অর্ডার ডেরিভেটিভ?
না, আমি কখন বললাম ডেরিভেটিভ? এগুলো তো কারেকশন টার্ম। এই যে ডেল্টা ইন এর মধ্যে এগুলো হচ্ছে কারেকশন টার্ম।
আর কারেকশনের কতটা তার থেকে ডেভিয়েট করছে?
হ্যাঁ, কতটা ডেভিয়েট করছে, ইটস নট দ্য ডেরিভেটিভ অফ ইন।
মানে কি এই ডেল্টা EN 0 বলতে হবে, মানে EN0 এর রেসপেক্টে কি বলবো?
না না, EN0 এর সঙ্গে এরা ইন্ডিপেন্ডেন্ট। আগের দিন তো দেখালাম যে EN0 এর সঙ্গে এরা ডিপেন্ডেন্টই নয়।
আচ্ছা,
এটা হচ্ছে কারেকশন টার্ম, দিজ আর দ্য কারেকশন টার্মস। মানে EN নট ছিল, সেখান থেকে এটা ডেভিয়েটেড হচ্ছে। তো আমি ধরেছি এই ডেভিয়েশনটা পাওয়ার ল অফ ল্যাম্বডা। যেমন পাওয়ার সিরিজ তোমরা ধরো যে A0 A1 এক্স A2 এক্স স্কোয়ার, তো এই ডেভিয়েশনটাকে আমি ল্যাম্বডার পাওয়ার লতে নিয়েছি। তো ল্যাম্বডার ভ্যালু যদি খুব বেশি হয় তাহলে হায়ার অর্ডার অব্দি নিতে হবে, ল্যাম্বডার ভ্যালু যদি খুব কম হয় তাহলে ল্যাম্বডা স্কোয়ার এগুলো নেগলিজিবল হয়ে যাবে, তাহলে ফার্স্ট অর্ডার অব্দি নিলেই হবে। এটা হচ্ছে আইডিয়া। এবং
এর সঙ্গে ফার্স্ট এক্সাইটেড স্টেট বা সেকেন্ড এক্সাইটেড
না না না, তো এন, সেই স্টেট তো ডিনোট করছে এন। এন এর ভ্যালু 1 হলে গ্রাউন্ড স্টেট, 2 হলে ফার্স্ট এক্সাইটেড স্টেট। সো দিজ আর দ্য কারেকশন টার্মস। দ্য গ্রাউন্ড স্টেট থেকে কতটা চেঞ্জ হবে, যেমন আমরা দেখেছিলাম যে স্প্লিট আপ হয়ে গেছিল, যেটা স্টার্ক ইফেক্টে দেখেছি। তো এইগুলোর জন্য স্টার্ক ইফেক্ট আছে, মানে এটা এক্সাইটেড স্টেট নয়। ওকে, ওকে, so these are the perturbation expansion, you can say. uh, these are the perturbation expansion, okay, of states and the energy eigenvalue, and you can put these things in the Schrodinger equation, and the Schrodinger equation is, what is Schrodinger equation? H naught plus lambda of h prime, uh, operated over n naught plus lambda n1 plus theta of lambda. I am taking higher order of lambda. Okay. So you can take one more term for clarification. Suppose lambda square of n2 plus theta of lambda. Okay. And this is equal to En. En means En naught plus lambda En1 plus lambda square En2 higher order of lambda operated over that n naught lambda n1 plus lambda square of n2 plus higher order of lambda. So this is the Schrodinger equation. Okay. Now in this equation you can collect the coefficient of different power of lambda, because it's a power series, and within a power series the different power terms are mutually independent. So you can equate the coefficient of different power terms, and in that way uh, you can collect the coefficient of lambda to the power 0. Okay, you can collect the coefficient of lambda to the power 0. Okay, so collecting the coefficient of lambda to the power 0, from here you have h naught of n naught is the only term having lambda to the power 0 term. So h naught of n naught equals to, from the right hand side only one term, en naught n naught. Okay, so en naught n naught. So this is basically the unperturbed Schrodinger equation. This is trivial. So the coefficient of lambda to the power 0 will yield just the unperturbed Schrodinger equation. Okay. Then in the next power term, lambda to the power 1. So from here you can get, from here you have h naught of n1, right? H naught of n1, h naught of n1. Then you have h prime of n naught. Okay, plus h prime of n naught. From the left hand side, only two terms are there. Only two terms. H naught over that term, and another term comes from this one, h prime of n naught. And in the right hand side, you have en naught over n1. Okay, so you have en naught over n1, then en naught over n1, then en1 over n naught plus en1 over n naught, uh, nothing else, right? So these two terms only. So you can rearrange these terms and you can find H naught minus En naught over N1, right? H naught minus En naught over N1 equals to uh, En1 minus
H prime.
H prime over N naught. Okay. So this is basically from collecting the power of lambda to the power 1. Now try to collect the coefficient of lambda square. So it is a little difficult. So from here you have H naught of N2, right? H naught of N2. H naught of N2. Then H prime of N1, right? H prime of N1. So the second term will be H prime of N1. Okay. Then after that, from here, so we have two terms from the left hand side having lambda squared term. Now from the right hand side, you have En naught of N2. Okay, En naught of N2. So equals to En naught of N2. Then you have En1 of N1. So plus En1 of N1. Okay. Then En2 of N0, right? En2 of N0. So plus En2 of N0. Okay, and you can rearrange those terms by suppose H naught minus E1 naught over N2, okay, equals to En1 minus H prime of N1. Then you have En2 of N0. Okay, this is from collecting the coefficient of lambda square. And look at the sequence here. At the left hand side, the terms are fixed. H naught and H prime, one having second order correction and another having first order correction. Look at here. Here H naught and H prime, one having first order correction and H prime having zero order correction. That means unperturbed correction. So if you take the coefficient of lambda to the power k, okay, if you take the coefficient of lambda to the power k, then you can definitely say that the term should be H naught of nk. Okay, H naught of nk. Then H prime of n k minus 1. Comparing those two, okay, equals to En naught. Okay, En naught of n2. That means En naught of it will be nk. Okay, then the term should be En1. Then the term should be En1 of n1. That means En1 of n of k minus 1. Okay, then the next term should be En2 of n k minus 2, right? And it will end up to En of k n0. Okay, like that. So the general term, that means the coefficient of lambda 2 here, the coefficient of lambda 2 uh, basically is this equation. Okay, so these are the outcomes from the Schrodinger equation in the part of situation. Okay, now uh, we shall analyze one by one. The first one is very trivial. This one is very trivial case. Okay. Which is part of Schrodinger equation. But you can effect or you can find the effect of perturbation. That means the non-trivial effect should start from the lambda to the power 1. Okay. So now I am writing the coefficient of lambda to the power 1, and which is basically you have h naught of h naught minus en naught. Okay. H naught minus en naught, right, of n1. Okay, h naught minus n naught of n1 equals to en1 minus h prime. ঠিক আছে, এখন থাক en naught minus sorry en1 minus h prime of n naught. Okay, so this is from first order coefficient. Okay, now hit this bra on the both side of the equation. Hit this bra. Then you have n naught of h naught minus en naught of n1 equals to n naught of en minus n1 minus h prime of n naught. Okay, so basically it will yield en naught. Okay, because n naught bra over h naught, it will yield en naught of n naught, because this is Hermitian. The original Hamiltonian is Hermitian, so those term will be 0. So then we have this one equals to 0. So this is a number, n1 is the eigenvalue, it's a number. Okay, so you can find n naught and n naught are orthonormal. So you will find en1 equals to n naught h prime of n naught. So this is first order correction in the energy eigenvalue. The first order correction in the energy eigenvalue, which is En1, which is nothing but N naught H prime N naught. And what is that? This is the matrix element of H prime. This is the matrix element of H prime, and the matrix should be represented in terms of the basis of unperturbed spectra. Okay, if you represent the matrix of H prime in terms of the basis as the spectrum of H naught. Spectrum of H naught means unperturbed spectrum. Then the first order correction in energy eigenvalue, which is NN matrix, the matrix element of the perturbing Hamiltonian. Those are the correction terms. Okay, in the energy eigenvalue. Okay. Now the second one, the energy states. So to find the energy states, so to find the energy state, I am going to operate some unity operator, and you know the form of unity operator. The unity operator I to be like summation over k. Okay, summation over k. First one will be kth, and second one will be bra. So this is the form of unity operator you find in mathematical tool of quantum mechanics. Okay, so you can operate this one at the both end of this equation. Then you will find summation over k naught. Okay, k naught of uh, h naught minus en naught, right? H naught minus en naught over 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 n1 n1. So this is n1. Okay, equals to uh, this one. This one should be uh, summation over k naught of en1, right? en1 minus h prime of n naught. Okay, so this is a number. So you can split this one in two terms. So the first term k naught en is a number, so k naught and n naught they are orthogonal. So you can connect k naught and n naught because k naught and n naught equals to 0. So this will go on. First term will go. Okay. Then you have only uh, this one, and here also you have ek naught. If you operate h naught on k naught, it will yield ek naught. Okay, so on the left hand side you have summation over k naught, and then you have ek naught. Okay, you have ek naught minus en naught, right? Ek naught minus en naught, and then k naught over n1. Okay, k naught over n1. This is equals to summation over k naught of k naught h prime n naught with a minus at the front. This minus was entered. Okay. Now this one and this one over k, it will yield the unity operator. So I operating over any quantity will yield that quantity. So you can write n1 equals to summation over k. Okay, and this term is nothing but H prime of Kn, the matrix element of H prime. And if you express the matrix of H prime in terms of the initial basis, then this is H prime of Kn over K naught by uh, Ek naught minus En naught. Okay, Ek naught minus En. And of course, here you have to apply the constraint K not equals to N. Because if you apply K equals to N, then those term will blow up. So you have to put this constant that K not equals to N. So this is the correction in the first order. Okay. So this is the first order correction in the Kate spectrum of the system. So then you can write En lambda. En lambda equals to, first term will be En naught, then lambda of H prime Nn, okay, then higher order of lambda, and N lambda equals to N naught plus minus lambda summation over K, K naught equals to N, H prime of Kn of K naught by Ek naught minus En, and then higher order of lambda. Okay. So that is the first order correction term in energy level, and this is the first order correction in the wave function. Okay. So similarly, you can use the second order correction term. Okay. From the dependence of lambda square, you have to collect this equation, and you can use the similar kind of operation to find the second order correction. And I am going to give you the homework. Okay. So this is homework for you. Find out the second order correction. Second order correction terms. Okay. So this is first order up to first order. Okay. Now we have some important information from this correction term. So if you see the correction term En1, which is H prime of Nn, the diagonal element of perturbing Hamilton. So if the perturbing Hamiltonian is unperturbed, then there will be no correction. At least up to first order. Okay. So for off diagonal perturbing Hamiltonian, you don't have any correction term, at least up to first order. And second one is first order correction in wave function, which is K not equals to N. Okay, and then you have, suppose, H prime of Kn, K naught by Ek naught minus En naught. So the whole correction terms depends on the matrix element of the perturbing Hamilton. Okay. Okay. So this is our non-degenerate perturbation theory and its development, and we have shown the correction terms up to first order. And now The job is in your hand to find the second order correction, which will be homework for you. Now, I want to give you some example. Okay. Suppose you have a system with unperturbed Hamiltonian H naught is equal to like that. Suppose this one 1001. Okay. And you have the perturbing Hamiltonian. It's suppose like E prime 0110. Okay. So literally, if you observe carefully the unperturbed Hamiltonian, you will definitely see it's the degenerate system. It's degenerate system, right? It's degenerate system. Hmm? Okay. Why degenerate? Because the eigenvalues
One.
is same E and E. Okay, so H naught have two states. H naught have two eigenstates. One is 10 with energy eigenvalue E, and another is 01 with same energy. So this is degeneration. Okay. Now look at here. This is perturbing Hamiltonian. This is perturbing Hamiltonian. So the first order correction, if you want to find the first order correction, suppose so this is suppose E1 and this is suppose E2. So E1 and E2 are basically same. Okay. So this 010 state and 01 state are degenerate. Okay. Now suppose you want to find E11. So E11 should be H prime 11 and which is 0. The diagonal terms of this perturbing Hamiltonian is 0. So this is 0. And also E21 is equal to H2 H prime 22 which is 0. Okay. So this is very interesting because you don't have the correction at least up to first order for this perturbing Hamiltonian. Okay. So as per our theory, that means as per our development or tools which I have already derived in the previous section,
Second order থাকবে না?
you can check up to second order, but at least up to first order you don't have any correction. Okay,
Second order
my opinion is clear. Okay, okay, you may have a deviation in the second order, but my opinion is up to first order in bare eyes you have no deviation in the energy correction. But if you want to find the eigenvectors and eigenvalue of the total Hamiltonian, here total Hamiltonian H is equal to H naught plus lambda H prime. So which will basically yield E lambda E prime lambda E prime E. So if you could find the eigenvectors and eigenvalues of this matrix, you can try. You will find some mesmerizing result. Okay, you will find two states. First state, one state suppose it will be 1 by root 2 1 1. You can check that one. The state will be like that. Okay, okay, because this one are eigenvectors, and the second one you will find it will be 1 by root 2 1 minus 1. Okay, and the eigenvectors are those are the eigenvectors with eigenvalue E plus lambda E prime, and this one is E minus lambda E prime. So the result is different. The result is different from here. From our approach, which I have already derived in the non-degenerate case, it will say that there will be no correction in the first order, at least up to the first order. But if you want to find the eigenvectors and eigenvalues directly from the Hamiltonian, you have found the eigenvectors which are also different from the first one, and the eigenvalues, energy eigenvalues, is slightly changed, and it will change up to E plus lambda E prime and E minus lambda E prime. That means it shows the first order corrections. Okay, so uh, this theory could not reach up to that effect, could not reach up to that effect. And we can conclude that for such system where the unperturbed states are not non-degenerate, they are degenerate, you cannot apply the previous methodology. Okay, you cannot apply the previous tool. So for degenerate systems where the unperturbed states are actually have the same energy eigenvalue, you have to develop different kind of methodology or different kind of tool to find the effect of that perturbation. You can use the non-degenerate formula. So the formulas for non-degenerate perturbation theory can be limited for the non-degenerate case. For degenerate case, you can apply those formulas. So you have to develop separately for the degenerate system. Okay, so the method to find the effect of perturbation will be different for degenerate case. Okay, so it is clear. Now you can also find more information from this example. If you can check that one, this is after perturbation, right? This is after perturbation. Before perturbation, the states, suppose in one knot, which was actually 1 0. Okay, this is 1 0, 1 0, and 0 1. Okay, so before perturbation, the spectrum was 1 0, and this one suppose 0 1. And after those were before perturbation, and after perturbation, it will change up to 1 by root 2 1 1. Okay, and it will go to 1 minus 1, and in that process, due to the perturbation, the degeneracy is broken. Before perturbation, those two states have the same energy eigenvalue, and after perturbation, you can clearly see that the energy eigenvalue will be different. That means the degeneracy will be broken. Okay, so look at here. You can express the perturbed state or perturbed spectrum as the linear combination of the unperturbed system. You can definitely write. You can definitely write 1 is equal to 1 by root 2 1 0 plus 0 2 0. Okay, because 1 0 means this one plus this one, that means 1 1, 1 by root 2. Okay, and 2 is equal to 1 by root 2 1 naught minus 2 naught. So clearly, the perturbed spectrum will be the linear combination of the unperturbed spectrum. So this is the way of understanding how we can proceed in the degenerate case. So this will give you the hint. How can you develop the non-degenerate the degenerate perturbation theory? And the hint is, if you want to break the degeneracy, then you have to make the changes in the basis. Okay. Previously, you have written the whole system in the basis of unperturbed spectrum. So due to perturbation, the basis will be changed, and the basis will be changed, and the linear combination of initial basis will yield the perturbed basis. Okay. So, so this is the fact for degenerate case, degenerate system. Okay. So taking that message from the previous example, we are going to develop the degenerate perturbation theory. Okay. So now, if you want to tally the degenerate system having the unperturbed Hamiltonian is not, then you have some matrix representation, which will be, suppose, E1 naught, E2 naught, E3 naught diagonally, and others will be 0. And as this is a degenerate system, then you can write E1 naught less than E2 naught less than E3 naught less than, suppose, EP naught, then equals to, suppose, EP plus 1 of naught, and it will go to equals to EP plus N naught, and then less than that. That means some of the states have the same energy eigenvalue, and those are the degenerates. Okay, and those are the degenerates. And the problem with degeneracy is that if you look at the first order correction for non-degenerate case in the state, it is minus summation over k not equals to n. This was, sorry,